Now we will continue our discussion on the first law of thermodynamics. This is related to our previous topic, or previous lectures that we tackled before. So now we are going to relate the first law in terms of mass. Now we will derive the conservation of mass equation. Okay, so we will define first the relationship between energy release and mass. And in this very well-known equation, wherein there is energy, wherein energy is mass times c squared, and you have mass is energy over c squared. So when there is energy release of a system, there is no change in mass. Okay. So we will consider now control volume here. Okay. So we have a control volume, and we have this one. And also we have this one. And our control volume, we have the given time t, and we have the mass t, right? Mass at time t, or this is the initial mass. So we have the external forces. We have pressure. We have this work. No, Q means heat, and we have this work that is generated by our control volume. So this is our pressure, and we have this area here at the inlet, and this is our exit point here. We have the pressure at the inlet, we have the temperature at the inlet, and the energy at the inlet, and the velocity at the inlet. So this one is the partial derivative of our mass at the inlet. This is the partial derivative of our mass at the exit point. And of course, this is our system boundary here. That is our system boundary and the control surface. Okay. Of the control surface. Okay, given time t, here, we have the mass t, mass at time t, this is the mass inside the control volume. Mass inside the control volume at time t. Okay. So in here, the mass is right at the boundary, the system boundary. So this is at state at a given time. There is mass at a given time. Okay. So, however, we will draw another control volume here, wherein the partial of mass is entering the control volume here. This is our mi, and the at the exit there is also mass at the exit. So we have other properties like this. There is pressure, initial pressure. We have the temperature, and we have the velocity, and the energy, and we have the pressure here, the temperature at the exit, and we have the energy at the exit, and we have the velocity at the exit. And of course, this is our system boundary and control surface. Okay, wherein we have the inexact, or we have the heat here, inexact differential of heat, and also we have this work. We have this work of our control volume, and also acted upon the pressure. So we have the mass T here, since we have mass entering the control volume and mass leaving the control volume. So this is plus inexact differential of T. Okay, so you have this energy total here, energy T, or energy T plus inexact differential of T. So take note, our time is T plus partial of T. Now this is an exact differential of T. It is at state 2, as you can see. So this is our state 1, wherein the mass is just at the boundary, it's the system boundary, and there is the mass is not entering our the control volume yet, and the mass is not leaving the control volume yet. On our state 2, the mass, there is entering mass, and the mass, there is the mass that is leaving here. Okay, so we have time T is T plus an exact differential of T, since we don't know what time, the given time. So in order to derive some equations, we need to use this notation here. So the mass mt here plus inexact differential of T, This is the mass inside our control volume. Mass inside our control volume. Okay, so at a given time t plus our time here, the given time t plus an exact differential of t. Okay, so the mass of the system here at state 2, you have the mass of the system, this is m2, so this is mt plus an exact differential of t plus what? V, an exact differential of m, that is leaving the control volume. Okay, so we can say that the m2 here, the m2 is equivalent to m1. Okay, so since we mentioned a while ago that the system, there is no change in mass, so when the mass at m1 is equivalent to m2, or the mass of the initial state of the control volume inside the control volume is equivalent to the mass of the final state of our control volume. Therefore, we have no change in mass. Okay, so here our m2 is mt plus an exact differential of t, and this is plus an exact differential of mass that is leaving, and here this is our m1 is equivalent to mt plus an exact differential of mass that is entering. Okay, so now we have to simplify this one. So we have here, we have this mt plus an exact differential of t minus mt. We need to transpose this one, so this is mi minus an exact differential of me, or an exact differential of mass that is entering minus an exact differential of mass that is leaving. Okay, so we will continue, and here mt, we have this mt plus an exact differential of t minus mi plus an exact differential of me minus an exact differential of mi. This is equal to 0. So we apply the limit here as this is t approaches to 0. Okay, so this is mt plus an exact differential of t minus m t here minus m t. Okay, this is mt. So here this is with respect to time. So this is d of our control volume, derivative of our control volume with respect to time. Okay, So the limit, we have the limit here. We apply limit here. The limit as t approaches to 0. So we have the mass and the differential of me over, or with respect to t, this is equivalent to me. And the limit as t approaches to 0, so this is the inexact differential of mi over inexact differential of t, so this is equivalent to mi. Okay, so therefore we have, as we going to substitute these formulas here to the above formulas from this formula here. Okay, so we have this one, the d n, or the, with respect to time, the differential of mass of the control volume with respect to time here, this is equivalent to, or this is plus the summation of mass that is leaving minus mass that is entering. This is equal to 0. So we have the summation of mass because we generalize the equation. Whether we have masses, we have a number of masses entering the control volume and a number of masses and leaving the control volume. So there is no change in mass, so that is 0. Okay, this is equivalent to 0. So this formula here, this is our conservation of mass, conservation of mass equation. Conservation of mass equation. So this is how we're going to derive the conservation of mass equation according to our first law of thermodynamics. So mass is being conserved, so there is no change in mass leaving and entering our control volume. Okay, thank you for watching, and that would be all. Thank you.